All right. So last session we had just begun with the introduction of field effect transistors. Very quickly we'll just go through the recap of what we had done in our previous class. Okay, so we had just looked at the chapter contents. Then we also discussed a little bit about the development of FET and the people who are actually responsible for the development of FETs. Then we also looked at the differences between a BJT and FET. BJT is a current controlled device, whereas FET is a voltage controlled device. Okay, we had also looked at the primary differences between BJT and FETs. Then we also looked at the symbols for N channel and P channel JFET. Well, JFET stands for junction field effect transistor. And there was a nice water analogy that explained how voltage actually controls in a JFET. Okay, so it is the voltage that is being applied at the gate that actually controls the current that flows from source to the drain. Okay, so that was the construction of a JFET. So we had seen that JFET is a 4-terminal device. Gate is the first one, drain is the second terminal, source is the third terminal, and substrate, which is actually not shown here but it is inherently present, is the fourth terminal. Normally we just mention only 3 terminals: gate, drain and the source. Okay, all right. So the major portion of the construction of a JFET consists of the N region, and on both the sides we have P regions which are being inserted through the doping process, so that we get 2 PN regions. So I'll just highlight it here. So that is the first PN junction which we get, and that's the second PN junction which we get, okay, upon doping. So whenever we say PN junction, then obviously there should be a depletion region present, which consists of acceptor as well as donor ions. Okay, so that's the depletion region present. Okay, fine. Right now the JFET is not biased. The moment we bias, the current starts to flow through the JFET. Okay, so let us just go through the next diagram. Right. So when VGS is 0 volts and VDS is some positive value, say for example plus 1 volts. Okay. In the yesterday's class we had to try to understand the operation of a JFET by considering the entire structure in a horizontal way. Okay. So here it is vertical. Okay. No problem. We'll just try to understand the operation and the working of a JFET with such orientation itself. Fine. So that's the source. I'll just highlight it, source, and that's the drain, and the third terminal which is gate. Okay. Right now gate and source are being shorted and are held at ground potential, so VGS is 0, and drain is being applied with some positive voltage with respect to the source. So drain is held at a positive potential and source is held at a negative potential, and it is just grounded. So everything, all of them are being grounded. Okay, so what happens in the last session we had seen that this PN junction, due to the applied polarity, gets reverse biased. Okay, because the drain region, which is of N type, is being applied a positive voltage, whereas the gate, which is of P type, is being applied a relatively negative potential when compared to the drain end. So obviously we can say that, just highlight it here, so this portion becomes reverse biased. Okay, so when it is reverse biased, we know that the width of the depletion region increases or enhances. Okay, now somebody may just ask me, sir, why is it that the width of the depletion region at the drain end is more bulged when compared to the width of the depletion region near the source end. Okay, well, near the source end, the source potential is same as that of the gate potential. Okay, so there is no change in the depletion region near the source end, whereas near the drain end it has just bulged. Okay, fine. So this has actually happened on both the sides, on the left hand side and also at the right hand side. Okay, now what will happen if VDS is further increased, say from 1 volts to plus 2 volts? Okay, that means we are trying to make the PN junction more and more reverse biased. So when it gets more and more reverse biased, obviously the thickness of the depletion region increases further. Okay, so I am just drawing it, how it increases. Okay, so this is what it happens. Okay, fine. So the point is the width of the channel. Okay, let me just denote the width. See, this is called the width of the channel through which the electrons are passing. Okay, so as and when the width of the depletion region goes on increasing, the electrons find it very hard to move from source to the drain end. Okay, so the point is the resistance offered by the channel goes on increasing as the drain potential increases. Okay, so you know that point should always be kept in your mind. Okay, fine. Let me further increase the drain potential to plus 2, I mean from plus 2 volts to maybe plus 3 volts. Okay, so what happens? Again, further the depletion region increases, and at some point of, or at some stage, it appears as if both the depletion regions are trying to touch each other. Okay, so this condition is called as pinch off condition. Okay, and I had already mentioned that so the voltage at which pinch off occurs is called VP. Okay, so during the pinch off the current saturates. Okay, so if I just draw the graph of the drain to source current versus VDS, so as and when VDS increases, initially there will be a resistance offered by the channel, but it will be linear. Okay, but after some time, due to pinch off, okay, pinch off is the state when both the depletion regions almost tend to touch each other. So after that the current just saturates, it becomes constant. Okay, now a very important point to be mentioned here is how does the current saturate, or why does it become constant? Okay, if the depletion regions would have really touched each other, then the current would have become zero. I repeat, right? Because the electrons would not have found any path to move from source to the drain, because the channel would have been completely blocked by the depletion regions. However, that doesn't happen. Okay, a very small passage always exists, right? So due to which the current just saturates. Now what if we further increase VDS? If I just further increase VDS from plus 3 to plus 4 volts, okay, what will happen? So that extra energy has to be reflected somewhere, right? Okay, if the depletion regions are not getting touched, then where is that extra energy getting dropped? That extra energy drops at the depletion regions itself, and that extra energy is being reflected as the change in the shape of the depletion region like this. Okay, that means the thin or the narrower channel goes on increasing. Okay, if I further increase VDS, it becomes like this. If I further increase VDS, again it becomes like this. Okay, so now the point is, I'll just try to give a very simple analogy. Okay, see, the stage when the current is increasing linearly, okay, the channel resistance will also be increasing, so that the current faces a repulsive force. Alright, but after pinch off, which is VP, I'll just draw the depletion region, how it actually appears. Okay, so this is how the depletion region appears. Okay, and the electrons have to move from the source to the drain end. Okay, and now the channel is extremely narrower. Okay, the n channel is extremely narrower. So what happens is, initially if there were 100 electrons moving from source to the drain, now even though VDS increases, due to the narrower channel, it is quite possible that instead of 100, see, all the 100 electrons cannot move now. Okay, because the channel's thickness is itself extremely narrow. So instead of 100, maybe just 5 to 10 electrons may move through the channel and enter the drain. Okay, now you may ask me, sir, then if the number of electrons have reduced, then will the current not reduce? No, the current will not be reducing. Why? Because we know that current can be expressed as I equal to it's okay, I is nothing but the rate of flow of the charges, right? It is rate of flow of charges. Okay, so the point is, these 5 to 10 electrons gain sufficient kinetic energy, so that they'll be moving from source to the drain at a very high velocity. Okay, at a very high kinetic energy, due to which they'll contribute the same current as that of the pinch off stage. Okay, so you should keep this concept in your mind always. Okay, so the point is, after saturation, it is just the few electrons that are moving from source to the drain through a very thin narrow channel with extremely high kinetic energy. Okay, alright, so this is at some fixed value of VGS. Alright, so let us try to move forward. Okay, so this is already been explained now, but the diagram is very clear, okay, so that it will be easy for us to understand. Varying reverse bias potentials across the PN junction of an N channel JFET. Okay, so the point is, here VDS is plus 2 volts. When VDS is plus 2 volts and when VGS is 0 volts, the depletion region at the drain end has increased. Okay, the width has increased, or the shape has got bulged, right? Okay, now electrons have to move from source to the drain, and the channel offers some opposition. Okay, so throughout the channel, whether the opposition will be the same? No, it will not be the same, because this actually behaves as if it is a resistance that is opposing, and it is not a single resistance, it is series of resistance, so that you can just observe. The point in the channel where it is highly reverse biased, there you have the largest opposition, okay, or the largest resistance. Then obviously the voltage should drop maximum there. So you can just observe, it is at this stage that maximum voltage is getting dropped, which is 1.5. okay, it's just an example. Further, the voltage drop is 1 volt. Further, it is 0.5 volts. Okay, so in that way the voltage gets dropped. Okay, and finally here it will be 0. Okay, fine. So the characteristics, well, okay, the same diagram which was previously explained, now it is more clear. Okay. That's the drain current versus the drain to source voltage when the gate voltage is 0 volts. So initially the channel offers resistance so that the current increases in a linear way. Okay, so you can just see n channel resistance is being offered. Fine. Once the depletion regions tend to touch each other, we arrive at the situation called pinch off voltage. Okay, so that's the pinch off. After pinch off, the electrons just move from source to drain with a very high kinetic velocity, so that the same amount of current is being contributed, and it is called as saturation current. So this is called saturation level. Okay, now the most important point here is, for amplification purpose, I'll just denote it, we usually use the linear region. Okay, so this is being used for amplification part, or to be specific, analog portion. Okay, we usually use this region, whereas for the digital portion, for digital applications, we usually use the saturation part. Okay, because at the end and here we'll be getting two logic levels, right? So this is, if I consider this to be logic 1, then I can consider this to be logic 0. Okay, I'm talking about the lowest range, okay, where there is no current. So this is logic 0. So I can use this portion for the digital applications, whereas the linear portion can be used for analog part. Okay, fine. So the pinch off region is again explained here. You can just observe in this diagram, both the depletion regions appear to be touching each other, but in reality they are not joined. There is extremely small narrow region appearing. Okay, you should be very careful. Okay, there always exists a narrow path. Fine. So that's the same condition. When does the pinch off occur? Pinch off occurs when VGS is 0 and when VDS equal to the pinch off voltage. Moving forward, beyond pinch off, what happens? Okay, so let me just go back to the previous diagram. I have just told that this region, the current is constant. Current is constant. So when the current is constant, can I not use it as a constant current source? Okay, I'm talking about only this region, the saturation part. Yes, it can be used. Okay, so the same thing is being displayed here. Beyond pinch off, the device, the JFET device in the saturation region behaves as if it is a constant current source. Okay, wherein the drain the drain current is equal to the saturation drain to source current. So ID stands for drain current, IDSS stands for drain to source saturation current. So I'll just write here, IDSS represents the saturation drain to source current. Okay, fine. So that is, if I just want to represent it in terms of characteristics, so that will be the linear region and this is the saturation part. So here I'll be having pinch off VP. Okay, so in this region the device behaves as if it is a constant current source. Okay, so that is beyond pinch off. Fine. Okay, so moving next, what happens when VGS is lesser than 0? So far whatever we have discussed was under the condition when VGS was equal to 0. Okay, so now what may happen to the current characteristics when VGS is lesser than 0? Okay, so I'll be asking a question here to the students. See, can you tell me, what I'll do is I'll just draw a graph here and maybe based upon that you can just respond. Okay, I'll be drawing the graph of IDS versus VDS. Okay, and this is the graph and the condition is when VGS is equal to 0. Okay, and here is our pinch off Vp. Okay, now if I just reduce VGS lesser than 0, say for example let us assume that VGS is minus 1 volt. Okay, so where should I represent the current now? Will the current be higher or lesser when compared to the situation when VGS was 0? I am asking this question to you students. Maybe somebody can just respond. Will I be getting a higher current or will I be getting a lower current? Students.
Lower currents.
Lower current?
Yes, sir.
Yes, exactly. Okay, very good. And why is that so? The reason is, if I reduce VGS, okay, then this PN region will get more reverse biased when compared to the situation when gate to source was 0 volts, right? Okay, in that situation also this PN junction was reverse biased, but now if I further reduce VGS from 0 to minus 1 volts, then the reverse bias is strong enough. Okay, and when it is more stronger, it is quite obvious that the pinch off condition will be reaching more earlier when compared to the previous VGS, previous gate condition when it was VGS equal to 0, right? So that means when VGS is minus 1, the depletion region bulges rather faster when compared to the situation when VGS was 0. So what does that mean? That means there will be pinch off earlier in this case, okay, when compared to VGS equal to 0. So when pinch off occurs much earlier, then it is quite obvious that the current flowing from source to the drain should also be lesser, right? The electrons which are flowing from source to the drain will also be lesser. So in that case, I have to draw the graph like this. Okay, just observe. So this is when VGS is minus 1 volt. Okay. Further, if I increase VGS from minus 1 to minus 2 volts, again I will be having a lesser current. So this is when it is minus 2 volts. Okay. Further, if I just increase, again I land up here minus 3 volts. If I further increase it, say minus 4 volts, I will not be having any current at all, or a very small current will be flowing. Okay, so the point is, will the pinch off voltage remain the same in all these 4 cases? Students, I am asking you the question. If I increase VGS from 0 to minus 1, minus 2, minus 3, minus 4, will the pinch off voltage remain the same? No, it will not remain the same. Okay.
No.
Yes, it will change, right? Okay, and the change is like this. Okay, see, when VGS was equal to 0, pinch off was here somewhere. When VGS is minus 1, pinch off will be here somewhere. Minus 2, it is here. Minus 3, it is here. Minus 4, somewhere here. Okay, so that means the pinch off will also reduce accordingly as my VGS increases in a negative fashion. Okay, so let us try to make the things more clear by observing this diagram. Okay, so please focus on this diagram. So that's plot of ID versus VDS itself. Initially when VGS is 0, you can observe that VP is somewhere here. Okay, a vertical line is being drawn. So this is pinch off voltage for VGS is equal to 0 volts. Next, when VGS has been increased to minus 1, okay, you can observe that a lesser current flows, right? Because the pinch off occurs much earlier. Okay, it occurs much early. Then further, when VGS is minus 2, again lesser current with pinch off occurring much more earlier. VGS minus 3, much more earlier, and then finally when VGS is minus 4, equal to pinch off. Now there is one point to be understood here. Okay, see, when I consider the graph, the first graph, okay, the largest current when VGS was equal to 0. Okay, in this case pinch off is with respect to VDS, right? Okay, I am just drawing a vertical line so that VP, it is the pinch off voltage when VGS was 0 volts, right? Now I am just increasing the gate to source voltage, okay, so that I'll be getting lesser and lesser current, and finally when VGS was equal to minus 4 volts, the current became 0. Okay, right? So you can just cross verify the things here. Okay, see, this point is again when VDS is 4 volts and this is equal to pinch off. Okay, and this is the stage when VGS is equal to minus 4 volts and this is also equal to pinch off. Okay, this pinch off, I'll just draw it here. You should understand the concept. Okay, when VGS is fixed, when it is fixed, and if I just go on varying VDS, okay, again the depletion region will get more and more reverse biased, so that at some point of time they will just appear as if they are touching each other and pinch off happens. But here pinch off happens only because VDS is increasing, gate voltage is fixed. Okay, but indirect meaning is that relatively the drain voltage is increasing with respect to gate. Okay, so that is first condition. Now the second condition is I am going on varying the gate voltage now from 0 to minus 1, minus 2, minus 3, minus 4. Okay, so that means lesser and lesser drain current is flowing because the depletion region is getting more and more bulged. Okay, and at some point of time the current will be almost 0. Okay, so this is also called pinch off. Fine. Okay, and IDSS stands for the drain to source saturation current. Fine. So moving next, if I just take a graph like this, okay, that resistance V equal to IR, so therefore R is equal to V upon I, and in this case it is VDS upon IDS. Okay, so if I just take a plot of VDS upon YDS, I'll be getting the resistance associated. Okay, so that particular resistance is being coined by a formula which is represented like this, where RD equal to R0 1 minus VGS upon VP, where VP stands for pinch off voltage. Okay, so you can just observe R0 is the resistance when VGS is 0, so this 0 indicates VGS is 0, and RD is the resistance at a particular level of VGS. Okay, so this problem will help you while solving some of the problems in our future classes. Then coming to the P channel device. Okay, to put it in very simple words, the phenomena is exactly the opposite as that in the case of a N channel MOSFET. Okay, so in short, let me just explain. The construction of a P channel JFET is same as that of N channel. The only difference is the type of regions. In the N channel, the channel was of N type. In the P channel, the channel is of P type. Okay, the doped regions in N channel were P. Here the doped regions are of N type. Okay, further here the current is due to holes. For a n channel it was due to electrons. Here the current is due to holes. Okay, and the polarities are also different, and the current, the flow of the current, its direction is also opposite. For a n channel it was into the device, okay, whereas for a p channel it is out of the device. As simple as that. Okay, so you can just go through this, understand it, analyze, and then you can interpret the things. Okay, one important thing which happens in the case of a p channel JFET is, it also happens in the case of n channel also, but just to put here the things in a very clear way. Okay, just observe. Let me just go back to the previous n channel characteristics. So here VDS is positive. Okay, let me just state VDS is positive, and the gate voltages starts from 0 and they are all negative for a n channel. Let me just go back to the p channel. Okay, so just observe. So it is again the same thing, ID versus VDS. Here VDS, the increments are negative. Okay, negative increments, right? And it is quite obvious why is VDS negative? Because just observe, the channel is of p type. Okay, if I apply a positive voltage to the p channel, then it will not get reverse biased. I'll have to apply negative voltage to the p channel, right? Okay, so you can just observe it. I am applying negative voltage. The symbol is wrong here. It should have been negative. Okay, so this should have been negative and this should have been positive. Okay, fine. So that's an print error in the textbook. Okay, fine. So I'll be applying a negative voltage, right, so that the PN junction gets reverse biased. Okay, fine. So due to that reason VDS is in negative increments. What about VGS then? For a n channel VGS was increasing in a negative way. Here VGS has to increase in a positive way. Okay, fine. If VDS is increased beyond certain range, which is called as VDS max, okay, beyond a certain range, then there will be breakdown happening wherever the PN junction is there, because the PN junction will be reverse biased, and we know that by the fundamentals of the diode. Okay, I just draw it here. So that's the diode forward bias characteristics, and the reverse bias characteristic, very small amount of reverse current will be flowing. But if you still go on increasing the diode voltage, if you just go on increasing the reverse bias, then something called as Zener breakdown or avalanche breakdown happens, due to which there is a sudden surge of current, right? So which is very bad for the device. So the same thing also happens here. Okay, so you are observing that there is a sudden increase in the current. Okay, so this is bad for the device. As far as possible, we'll try to restrict this. Okay, fine. Okay, so moving next is the transfer characteristics. Okay, a transfer characteristics gives the linear relationship between IC. Just a second. Okay, so the transfer characteristics gives you the relationship between the drain current and the gate voltage. Okay, so I think we'll stop here, because okay, we'll just stop here and then we'll try to continue with the transfer characteristics in our next class. Okay, fine, because it will take me at least 15 to 20 minutes of time to cover this topic. Okay, so we'll stop here as of now. Students, if you have any doubts, then you can ask me.